Alright, let's go to part 3. Start looking at H-bridge design. This is just sort of an overview of the way I look at the world anyways. It's pretty straightforward. In any H-bridge, it's a bidirectional circuit that enables voltage to be applied across a load in either direction. So you can use it for a DC motor or stepper motor or single phase even or three phase motors. H-bridges are common to all VFDs or variable frequency drives out there. So on the previous video I had shown you a stepper motor driver like this guy that has an H-bridge built into it. In this video I'm going to show you a discrete H-bridge that I've built up for that. So you can make it out of relays, you can make it out of any kind of switch. Basically, what an H-bridge is 4 switches configured like an H, and with the motor going across the middle branch. In this case, we're using a DC motor for the example. So you can see that if you were to switch this guy on and this guy on, like so, you would have current flowing through the motor from positive to negative, and it would be going in the forward direction. If you wanted to reverse the motor, you would have to do the opposite. Switch this guy on and this guy on, and you would now have current flowing the opposite direction to reverse a DC motor. It's pretty simple. This is, in a sense, you can put JFETs or MOSFETs or IGBTs in the circuit, and boom, you could have an H-bridge. Well, sort of. In this one, you're seeing N channels being used. This, as it is, you would think you could hook up a micro to each of these pins and control them and figure out how you want the motor to work, pulse width modulated, whatever, but it won't work. And I'll kind of explain why. So it has to do with what side of the bridge the switch is on, or the FET is on. And so there's a high side and a low side. The side being connected to the positive rail will be the high side, and the side being connected to the lower rail will be the low side. So in this, you would have a high side switch. So here's an example of a high side switch, where the switch is above, as far as the rail goes, positive rail goes, the load. So in this example, we got a P FET. And so when you have a micro pin controlling this guy, you would pull it low, and this would pull away the current and turn this guy on, essentially, turn the load on. So on a low side switch, you'd have the load above from the source, the load, and the switch. In this case, we've got an N channel FET, and the N channel FET, again, the high would turn it on. Otherwise, with a P, it would be a low that would turn on. So that's what a high and a low side is. Basically, the low sinks the current, and the high sources the current. So, high switch. On the high switch side, which is the more complicated part of an H-bridge, do you want an N or do you want a P channel? Well, classically, they've been designed with both. They just both have positives and minuses. The higher resistivity of a P-type silicone puts it at a disadvantage to the N-type. Basically, it's a higher resistance, so it makes it more difficult and more prone to heat. So getting the N-type performance out of a P-type FET usually means larger geometries. You've got to make it bigger to handle it. So a P FET and an N FET will have to be different sizes if you want to pair them together. So rule number 1. This is one of my rules I've learned by trial and error and a lot of things blowing up. The MOSFETs have a maximum voltage to gate, or gate voltage to source, VGS. Beyond that, you let the smoke out. MOSFETs, like most electronics, require the smoke to be inside to work. MOSFETs have gate voltage thresholds at which they turn on, and a separate voltage at which they turn off. So if we take an example of like an IRL 530, typical guy, you can see here that, you know, he's got his VDS, his max is 100 volts. He has a specific pattern. It's an N-channel MOSFET. Key thing is when you look at the voltage to gate to source, plus or minus 10 volts limit. So if I put more than 10 volts from the gate to the source, I will cause problems with this FET. The smoke will stay in if VGS is less than plus 10 volts for an N channel, minus 10 for a P channel. Alright, so that's an important thing. So where it is in position-wise matters, because you'll see in a second why. MOSFETs, rule number 2. MOSFETs have a gate voltage threshold in which they turn on, and a separate threshold in which they turn off. Makes sense. Just like any TTL device. If you apply, in this case, 2 volts to the gate with respect to the source, the IRL 530 will allow current to flow from its drain to its source. So you need 2 volts. So here are the typical curves for a VGS versus the ID current. So this is showing that essentially in a nonlinear fashion, the more VGS, the more drain current. And same here, you see the ID current versus the voltage from drain to source. It steps up and then it flatlines like a transistor curve, standard transistor curve, which I'm sure you're familiar with. So here's the rub. For N channel to be on the high side, you will need the VGS threshold plus the voltage on the source to turn on the MOSFET. Okay, let me repeat that. If your source voltage of the motor is above ground, which it will be in a normal configuration, you need that plus whatever the turn on threshold is to turn this guy on. So if switch A is conducting, in this case this is switch A, the voltage at the source of the motor, V+, in order to keep the ID current flowing you will have to have a gate voltage of VGS threshold, like 2 volts, plus the motor voltage. Alright, so motor voltage is the rail. See where we're going here? If the motor voltage is 24 volts DC, and the gate threshold would need to be at least 26 volts. Hence, you'd need a charge pump to get this guy to turn on. You need to go above that voltage. For P channels, it typically requires a negative voltage, but that's just relative to the orientation of the switch. The VGS has a maximum value. Remember, it's negative. It's still the same concept. If the source voltage is higher than the VGS max, then the gate drive cannot be 0 or lower without blowing the FET. You can get a PFET with a high max VGS, like plus or minus 30 volts. That would help solve the problem. But if your source voltage is higher, you will need to add a Zener diode in something like this configuration. So this is my micro switching on anything really. It could be an NPN. The Zener diode voltage drop, which will be within the limits of the VGS threshold in order to turn that guy on. But you'll still have the 0.2 volts or lower, maybe 0.1 volts across here to turn it on. So turning off with a fixed voltage that doesn't hurt the VGS threshold, and on with a low voltage from the transistor. Here is my H-bridge prototype. And I will have another video showing the schematic for this. But in a nutshell, I've got a P and an N on either side of the bridge feeding my fancy little motor here, which is from a blender. I have got a PIC, DSP PIC 30 on there, and a little touch interface screen here that I'm still programming. I've got a linear regulator for the 5 volts with this sort of Frankenstein dropping resistor, and I've got a fan to keep it cold because I'm dropping quite a bit across a very small regulator. So turning it on, that's the fan noise. And I've got my little program here, blue for manual, and so I'm in manual mode now. And if I push it, I get my motor to spin one direction. And I've got a relay here that allows me to switch the direction. Again, this is a universal motor, so I have to reverse the windings to make that happen. But in the next video, I'll show you what the exact circuit of that is and how it works. I've also got my encoder on here, kind of loosely coupled right now with some heat shrink, just counting the pulses as I turn. So I will get into what I'm trying to do with this later, but ideally that's how an H-bridge works.